Good afternoon. My name is Mads Peter Andersen. I work at Aalborg University in Denmark, and I'm here to present our work on quantification of T-wave morphology. Inhibition of the rapid potassium current, IKR, is the physiological mechanism underlying both congenital LQT2 and most known cases of drug-induced 1QT. As Jean-Philippe Coderc pointed out just a few minutes ago, quantification of the resulting repolarization changes is an important part of pre-marketing testing of new drugs. The QT interval is an imperfect marker of this phenomenon, and the pharmaceutical industry is looking for new ways to quantify and assess the drug effect. And Selvich and co-workers have shown that IKR inhibition is not only expressed by QT interval prolongation, it also causes dispersion across the myocardium, resulting in T-wave morphology changes, in turn resulting in torsaphilin. So we developed a method for discriminating from the ECG between normal subjects and long QT2 patients. We published this previously, and now our next goal is to apply this to drug-induced 1QT. So we hypothesized that T-wave morphology parameters that discriminate well between healthy subjects and LQT2 patients are potential markers of IKR inhibition in drug-induced 1QT. So let's take a look at our method. The three prominent features that we see in our LQT2 population is the presence of asymmetric T-waves, the presence of notched T-waves, and also flat T-waves. So we, with this LQT2 population as a training set, we developed an automatic method to quantify these three features. Our asymmetry score compares slopes on both sides of the T-wave. Our notch score detects notches using the curvature function. And our flatness score is evaluated by means of kurtosis, a measurement of flatness known from statistics. So these are the results of a study of 30 LQT2 patients and 1,096 healthy subjects. As you can see, all three morphology parameters yield clear separation between the groups. I should probably go back because I forgot something. We also form a combination of these three, just a linear combination of the three. We call this the morphology combination score. That is shown here on the right. As you can see, the morphology combination score performs just as well as QDCF in separation between the groups. But very interesting, QDCF and MCS show only weak correlation, and the combination score is not at all as correlated with heart rate as the QT interval. So, to test our algorithm, we looked at data from drug-induced 1QT. It's a soda hole study. Soda hole is, as Jean-Philippe pointed out, a strong IKR inhibitor. And we looked at a study of 21 males, a baseline day, low-dose day, and a high-dose day. Holter recordings were made, and we sampled 10-second ECGs every 30 minutes. Yeah. Can we have the movie, please? This is a movie playing, showing an example of the effect of drug on the high-dose day in a single subject. You'll see how the change in soda hole plasma concentration is reflected on the T-wave shape. I'm just going to go over here and redo it. So, just pause the movie here. You'll be able to see how the T-wave appearance is very similar to that of the LQT2 T wave that I showed earlier. Then it returns to normal. So if we quantify this for the whole population, looking at mean trend curves for the whole population, we'll see that all three morphology parameters are clearly dose dependent. And if we look at the morphology combination score and QDCF, they both clearly show the drug effect. Green being baseline, blue, low dose, and red, the high dose. If we take a closer look at the morphology score and compare this with QDCF, you may notice that QDCF has broader error bars here on the baseline day than the morphology combination score. If we try to quantify this using effect size, which is a measurement of how many standard deviation our parameter moves away from the baseline recording, we will actually see that the response in MCS is double of that seen in QDCF, both on the low dose day and on the high dose day. And also, you see the dose dependence of MCS, double dose, double value. So this is a very interesting and important result because our data suggests that if we look at morphology instead of the QTC interval, we'll actually be able to have the variability, to get half the variability in our measurements. So, in conclusion, the morphology combination score performs just as well as QCF in detection of congenital LQC2. It's much less hardware dependent than the QC interval, and MCS is a more sensitive marker of soluble-induced IPR condition than QCF. What we see is lower baseline variability or a more prominent response, meaning larger effect size and more statistical power. So, summing up, we think that the morphology combination score may become useful in thorough QC studies in the future. Thank you.
The first question comes in mind how it is lead dependent, because what you showed looked like one lead.
Yeah, that's correct. We formed a lead very similar to that Jean-Philippe presented by looking at principal components. So
this is from the S1.
Yes. This is we make a XYZ transformation. Look at only the ST segments and use these to form a PTA-based lead. So we optimize for information from the ST segment. And this is the lead that we use. This gives us quite good stability in our measurements.
Just a question about the combination. What's your justification for combining them? I mean, in a sense, because you put the amplitude, you put morphological indexes. We did look at the amplitude in Sotala, and we found out that actually the amplitude is not related to heart rate anymore when you have IKR blockers, which is not true when there's no blocking. So I guess that if you would do, an analysis with each of them, you would find that most of them are not related to heart rate at all. It's just the relation you have, I think, is linked to amplitude of T-wave.
The amplitude of T-wave is the way that there are several questions there, as I understand. The way that we look at flatness of T-wave is not just T-wave amplitude. The T-wave amplitude measurement is very unstable compared to the way that we do it. Because we look at the T-wave as a whole, and by having several samples and when we calculate the shape,